Okay, so here, the next step here is just a property of expectation. When A here is just a constant, you can take constant of matrix, you can take it out of the expectation sign so that, but since the expectation of Z is just 0, so what we have is just mu. Now, using the following facts, so from theorem 1.10a, that the covariance of mu is 0 since mu is a constant, and the covariance of Z is I, then the covariance of Y so in general, you cannot do this as long as you are not assured that okay, covariance of X plus Y is not necessarily equal to covariance of X plus the covariance of Y. Assumptions of X and Y here to write equality is when they are independent, no? Now in here, since mu is just a constant, then you can do this, no? But in general, if X and Y are random variables, then you cannot do that. You cannot do that because there can be correlation between or association between X and Y. So naani siya plus factors. So it will be equal to the variance of X plus the variance of Y times 2 times a cofactor or a covariance between X and Y in general. So we can just do this because we know that mu is a constant. So from here, we have previous result that the covariance of this transformation pre-multiplied by a matrix A can be written in this manner. And the covariance is of a constant is 0. But this is equal to I, so what we will have is AA prime. So previous result shows that if you have a random variable X, which is normal, any transformation that is just linear will still be normal, no? So AX will still be normal, or pre-multiply by a constant is still normal. But later you will see that transformation of product of a normal is not necessarily normal. We will see later that a normal times a normal product na siya. Linear transformation, okay ra. Or pre-multiplied by a constant matrix or a constant vector. But product of random vectors will no longer be normal. You will see that it will be chi-square distributed later. So since this is just a linear transformation, then it's still normal, but the main vector will be mu, and the covariance matrix will be AA prime. So from Z, which is normal 0 of I, a transformation of AZ plus mu will be normal with parameter mu and covariance matrix AA prime. AA prime. So if we will let sigma to be AA prime, then a transformation of Y, AZ plus mu, will be this moment generating function. Okay, so a transformation of a Y, which is AZ plus mu, the moment generating. So ang Z na ay moment generating na e to the E T prime T over 2. In this transformation, the moment generating function will be So this is equal to wala na siya expectation. E to the t prime t over 2. But if in this transformation, the moment generating function is e to the mu prime t plus 1/2 of t prime sigma t. So naka-insert din himangod ganina din ha. Kay ang imuhang mu 0 raman. So mawala ni na term. But if it's not in general 0, so you will have mu prime t plus 1/2 of t prime sigma t. So this is the moment generating function for a random variable y, which is normal with mean mu and variance sigma. So variance will be sigma. So remember that. So the moment generating function for a standard normal will be this, and the moment generating function for normal random variable with mean mu and variance sigma will be mu prime t plus 1/2 t prime sigma t. So let's see some results. So this theorem, the proof of this theorem is similar to the illustration that we have just discussed. So if we have standard normal z, which is normally distributed with mean vector 0, and covariance, the identity matrix, then any transformation on z, which looks like y, that is az plus mu, then the moment generating function of y is given by the exponential of mu prime t plus 1/2 t prime sigma t. So for the proof, this is by definition of moment generating function. So a moment generating function of a random variable y is the expectation of the exponential of y prime t. How you define y prime, you substitute it there. And then by lemma 1.24a, previously, if you have this transformation, you can write the form as the exponential of mu prime t times the moment generating function of z. No, this is by lemma 2.1.24a. You can check. So if we look at that 1.24a lemma, here, no? So if you have this transformation, then the moment generating function of x can be expressed as the exponential of b prime t, atong dinhi, times the moment generating function of y at a prime t. So using that result, so you can write this linear combination here as the exponential of mu prime t times the moment generating of z at a prime t. But z is standard normal, no? Z is standard normal. So ang standard normal is e to the t prime t over 2, no? Pag standard normal. So you have 1/2, but imong t din he is a prime t. So that will be a prime t prime times a prime t. Or you can rewrite this as T prime, A prime prime, which is just A, and denoting this as your sigma. So you will have, and then joining again the exponential. So you will have exponential of mu prime T plus 1/2 T prime sigma T. So we see from this moment generating function that y is still normal, no? But the parameter now will be mu and sigma because this is unique. This moment generating function is unique for a normal distribution. And then a transformation of your y. So imong y kay ano man ni siya? Az plus mu. Az plus mu, and then kung minusan ni mo mu, of course may mo siyang az na lang. So we see here that this is still the y now, or y star will become normal, but the mean is 0 and the variance is sigma, no? Kay sigma diha. So this corollary, if we try to find the moment generating function of, say, x is y minus mu, then the moment generating of x will be given by this, no? So to do that, this is the proof. So dinhi ang atong transformation will be from a y normal mu sigma, and we do a transformation on y, which is y minus mu. Then x will still be normal, but the mean will be 0 and the variance will be sigma. This is what this corollary is telling you. So as a proof, this is just by definition of moment generating function. And then you can write this in this manner: y plus negative mu t prime, using again lemma 1.24a. So this is equivalent to this times the moment generating function of y. So this is using lemma 1.24a again, property of moment generating function when transformed as a linear combination. And then, but y here is normal with mean mu and variance sigma. So the moment generating of a normal distribution is given by that. So that's the exponential of mu prime t plus 1/2 t prime sigma t. And then joining again exponentials and separating that, but this is just e to the 0, which is equal to 1, which gives us this term only, no? So here. So this moment generating is telling us that if a transformation of y with a mean mu and variance sigma is done by subtracting it by mu, the new random variable will still be normal, but the mean will be 0 and the variance is still sigma. Okay, so the next theorem is 3.6 in Arnold. This is what the illustration was talking about. That is If that is normally distributed, then the mean is just mu and the covariance is just equal to 0. So let us assume from now that our y is normally distributed and do some transformation on this. The first transformation that we can do is when we pre-multiply y by a scalar c. So what will happen to the parameters mu and sigma? This theorem tells you that it becomes c mu and c squared sigma. So when we say c is scalar, so it is an element of R1. Okay. Now, let's find out the moment generating function of Cy. By definition, by previous result, what lemma is this? We have shown that earlier that if we do transformation 1.24. Okay, here. When we do transformation on a random variable by pre-multiplying it by a scalar, the moment generating function of the new random variable is equal to the moment generating function of the original random variable, but this time it will be at ct. So what lemma was that? That was lemma 3.4b. Okay. So this is lemma 3.4b. Okay, so moment generating function at t when your random variable is at cy will be equal to the moment generating function of y at ct. Now we know that y is normally distributed with mean mu and variance sigma. So for this particular, that will be the moment generating function at t, no? And the moment generating function at t will be e to the mu prime t plus 1/2 of t prime sigma t. Pero this time, it will be at ct. So it will be ct ning mga t din ct. So it will be mu at ct plus 1/2 ct prime sigma ct. So mu and c are just constant, so you can take it to be together because c prime prime is just also equal to c, so it doesn't matter. So you can join this together to be your kaya ang itsura dapat sa imuhang moment generating function dapat mu t para mu prime para maitsura nimo na mao ni ang imuhang mean vector. So c placed here, c mu t and mu prime, pero gusto nato na ang mu naka-prime but doesn't matter. C prime prime is just a constant, so you can have it in this manner. That is equivalent. And then you will have here t prime, c prime, and c, but c prime is just c, so you will have c squared because that is just scalar. sigma t. So, kini ang imuhang covariance matrix. Kini ang imuhang mean vector. So that Cy will be normally distributed with a mean C mu and a covariance matrix C prime sigma. Do you have questions?
Wala, ma'am. Okay naman.
Okay, so ang transformation atong gibuhat, y, so good, normal, mu, sigma. And then atong gi-cy, so this is still normal, c mu. And then c squared sigma, no? The next transformation that we will do is, this is just a corollary. So if we multiply it by not scalar but a vector a prime, so it will be a prime mu. And then ang c squared sigma t, ang c squared sigma din kung vector na siya, will be a prime sigma a. No? So kay kini siya, scalar na siya. So kung vector ang imong i-pre-multiply, the sigma will become a prime sigma a. Okay, so this result can be proven by following this proof, changing C to A prime. And then using the properties of covariance pre-multiplied by a constant, di ba? Ang covariance of A prime Y is equal to A prime YA, no? Man ang covariance later kung matrix siya is A Y A prime. Okay? Next. We start with this assumption that Y is normally distributed. You pre-multiply Y by matrix P by N. So this is conformable because your Y is N by 1. So AY, this is P by N, and then N by 1. So your AY will become P by 1. No? It becomes a vector. And you also add it by a vector B. So dapat P by 1 para conformable plus B, that is P by 1. No? So what you are going to produce is a P by 1 vector. So AY plus B is a P by 1 vector. So if you start for Y to be normally distributed, AY plus B is still normally distributed. So Y is P by 1, AY plus B is P by 1, but the mean will be A mu plus B, and the covariance matrix is A sigma A prime. Okay, so let's look at the proof. So it's telling us that the moment generating function when we transform Y into AY plus B is just equal to a constant here, which is the exponential of B prime T times the moment generating function of Y at A prime T. Okay. So we can use this result, no? Now, napakita na ni nato sa 3.4a. So if we use this result, then the moment generating function of x, which is ay plus b, is this constant exponential of b prime t. So why am I saying this is just a constant? Because b prime is p by 1. So b is p by 1. So b prime will be 1 by p. And t is p by 1. So this will just be a 1 by 1. So exponential of a 1 by 1 or exponential to a constant. So that is just a constant. And y is normally distributed. So kung normally distributed siya, naa siya moment generating function in anig forma. Pero ang imuhang t, in anig forma, pero ang imong t is a prime t. So you will have exponential. This is the moment generating function of a normal distribution. So this is equal to the exponential of mu prime at a prime t, plus 1/2 a prime t prime. So that this is the equivalent of t prime sigma t. Pero ang imong t din is a prime t. So a prime t prime sigma a prime t. And then what happened here? So this is exponential bt, this is exponential. You can put it inside. A plus b is just equal to a times e to the b. So originally, inani siya forma, giana na po nimo. Okay? And then joining these two. Is that the same? So this is a mu prime, a prime plus b prime. And this one can be written as a mu prime plus b prime. So it's just the same. Okay? So, ang imong tuyo ani maitsura gid siya na exponential of mu prime t plus 1/2 of t prime sigma t. So, kuha din mo ning mu. So, in terms of prime, so ang imong mu is a mu plus b. Man, ang imohang sigma din will be a sigma a prime. Okay? So that this will imply that x is still normally distributed, but the parameter now will be a mu plus b, and the covariance matrix is a sigma a prime. So from a y, which is normal, a transformation on y, say equal to ay plus b, will still be normal, but the parameter will be a mu plus b, and the covariance matrix will be a sigma a prime. Okay? Okay, a corollary, if we will just have an AY transformation, so you still have the same covariance matrix, but the mean vector will just be equal to a mu, because the mean of a constant is just equal to 0. So wala na plus b din. So that is a corollary, no? Questions so far? So inyong mabantayan ang transformation na atong gihimo from anormal and it becomes still anormal kung linear transformation lang. Either pre-multiply the vector, a normal vector by a constant, by a vector, by a matrix, or linear transformation, you add it by a constant b or add it by a vector b, no? So, normal lang gihapon siya. Pero kung product na transformation, lahi na po na pagka-istorya. Okay? Next. So this is a very important result. So we let mu be any n by 1 vector. We let sigma any n by n non-negative. So sigma here is just non-negative definite matrix. If this is assumed, then we can always find a y such that y is normally distributed. So kung naa daw kay vector mu, then naa kay na negative definite matrix sigma, there will always exist a y, no? Such that normally distributed na. So, unsa man na y? If we recall earlier, ang atong pag-define sa y is az plus mu, no? So, hinani na transformation, naagyo kay makita na normally distributed siya, no? So, az plus mu. Ang problema nato, unsa na ato ang a? So, later, para mahimo na siyang sigma, kanang a, kay, di ba, nakita nato na mahimo siyang a, kung unsa ang sulod dinhi, then a prime, no? Unsa ng a na atong inote, kay there exists man. So, ibig sabihin, maghimo ta, makahimo gyud ta, no? So, ang atong pilion na a dinhi is sigma inverse para mo gawas ning sigma. So, when we say there exists, ibig sabihin you can always find or there is a y that you can find that it becomes normal. So, for the proof, inana ang flow sa proof kung inyong tan-awon. Ang flow sa proof, this is the assumption, no? So let mu be an n by 1 vector and sigma is non-negative, so dapat na greater than, okay? Or equal. Greater than or equal man ang atong notation sa non-negative definite. Okay, so let Z be independent, standard normal kada isa. Then that is the vector itself is normal with mean vector 0 and 1. So dinhi na ang existence. You define a y equal to sigma 1/2 z plus mu. So if you try to find the expectation of y and the covariance of y, so kuhaonin mo ang expectation of y and the covariance of y, you will see, applying the previous result that we have, you will see that the expectation of y will be equal to mu because kini siya may mo man ang expectation is just 0, so mabilin si mu. And the covariance will be equal to A, I, A prime. But our A is sigma to the 1/2. So sigma to the 1/2 man I, sigma to the 1/2 prime, but sigma to the 1/2 prime is just sigma to the 1/2. Then sigma to the 1/2 times sigma to the 1/2 is just equal to sigma. So that's why this is equal to sigma. So ang nahitabo din actually is sigma to the 1/2 I sigma to the 1/2 prime. No? So that is AI A prime. But that is just equal to sigma. So let us look at this remark. So we see in theorem 3.6D, in a theorem, shows that the family of normal distributions is preserved. No? The family of normal distributions is preserved under linear operation. So, moto akong gingon, mag-start mo linear, mag-start mo normal. So, if you have a y, normal, mu, sigma, any transformation, as long as it is linear, say cy is still normal, pero mag-usab lang ang mga parameters. A prime y, it's still normal. Say AY is still normal. AY plus B is still normal. So even if this is a constant or that is a vector, no problem. Pero kung inani, kung matrix din pre-multiplied, dapat vector ni siya para conformable. Kung vector ni siya, vector po na, no? So, morning pasabot ani na remark. It is preserved under linear operations on the random vectors. Theorem 3.7 shows that it is preserved after undertaking marginal and conditional distribution. So this is theorem 3.7. So kung marginal o conditional distribution, you start with a normal, the marginal distributions are still normal po, no? So this is the next theorem. It talks about marginal distributions. So ibig sabihin, i-partition nato ang atong y as y1 and y2. But then again, recall that this is vectors, not a single y1 ha. Vectors. Ang y1 is vector na siya, ang y2 is vector na siya. So these are vectors. Suppose that your y can be partitioned into this, wherein your y is normally distributed. What we want to know is what will be the distribution of y1 and what will be the distribution of y2 if we partition our random vector y into y1 and y2. So if we will partition y into y1 and y2, we also partition our mu into mu1, mu2, and our covariance matrix will be, you have the diagonal matrix here, sigma 1, 1, sigma 2, 2, and covariance matrix here. This is symmetric, so whatever is the entry here, it's the same as the entry here. So if y1 is p by 1. So this is p by 1. Sigma 1, 1 is p by p. So kung si y is n by 1, n man eh. So ang mabilin kang y2 is n minus p because ang p na akang y1. So si y2 is n minus p ang dimension. So y2 will be n minus p by 1. No, mao na ang dimension ni y2. So if our y is normally distributed, the marginals also are normally distributed. Okay, so you can prove that, or you can show that by getting the moment generating functions of y. Normal man siya, so naa siya moment generating function. Again, moment generating functions are unique per random variable. So kung normal, na siya iyang kaugalingong moment generating function. So if we had partition y into y1 and y2, t gets the dimension of y also. So we can partition t as t1 and t2. So here. So t is also p by 1. Kaya mauman ay dimension sa y1. So the moment generating of y at t, mag-partition nato si t, ana, no? Or you can write it as the moment generating function at t is equal to the moment generating function of t1, t2. So this is just to rewrite it na pahigda, no? But actually inani na siya. So in general at t, kung normal siya, it's the exponential of mu prime t plus 1/2 of t prime sigma t. Pero subpartition man nato og t1 and t2. So unsay mahitabo ani? So mu prime exponential of mu prime at t1 t2 plus 1/2, and then t1 t2 prime sigma, and then t1 t2, or equivalently this is equal to mu prime t1 plus mu prime t2. Pero ang atong mu i-partition po na nato og mu1 mu2. So mao na mahimong mu1 mu2, no? Pag ana nato kay kining mu prime nato is mu1 mu2 man na siya. I-partition po nato. Kung i-partition na nato, i-partition po nato si mu1 mu2. So mahimo siyang inani, so mao ni na factors dinhi kana. And then kini mahimo na siyang t1 t2, then sigma, pero imong sigma ang forma niya inanig itsura kana. So kana ang imong ibutang dinhi. And then t1 t2. And then pag multiply nimo ana, you will get this star. So let me erase some parts here. So kini na part din he. Kung ilisan nimo ni og kato iyahang notation sigma 11, sigma 22, sigma 12, sigma 21, and then do this. So multiply na diha. Then kana pagkaman ang result, i-multiply na pod ani, you will have this. Okay? So the moment generating function of y, when we partition t as t1, t2, partition mu as mu1, mu2, and rewrite your covariance matrix in this manner. So you will have this moment generating function here. So the moment generating function will be equal to that, where star is equal to this. So when we want marginal, y1 lang, the marginal will be when t2 is 0. So ibig sabihin, mas 0 ni. Everything with t2 is 0. So what remains is this one. This is also 0 because that is T2. So kiniray mabilin. But this is the moment generating function of a random variable with mean mu1. So this is normal with mean mu1 and covariance matrix sigma 1, 1. So we have shown this, no? Okay, mao man na ang moment generating function na ang mean niya mu1. Ini siya, mu1. Ang covariance matrix niya is sigma 1, 1. So that's the conclusion. And similarly, again, using this result here, letting T1 to be equal to 0 will give you the marginal moment generating function for Y2. And you will see that it is equal to, it is normal and minus P na siya with parameter mu2 and covariance matrix sigma 2, 2. So preserve gihapon ang pagka-normal sa random variable even if we are looking at the marginal distribution. Next, if and only if statement, but we can show this both ways. So suppose that Y1 and Y2 are independent. So you have a result. Kung independent sila, then the moment generating function can be factored sa iyahang marginal distribution. So this was lemma what? So if you look at the book of Arnold, that will be lemma 3.4D. So if Y1 and Y2 are independent, then you can factor the marginals by the product of the marginals. You can have the moment generating as the product of its marginals. But this one from the previous result can be expressed in this one times this one. And joining the exponentials, everything in one exponential, you can have this one and this one. Note also that if Y is normal, then the moment generating function of Y can be expressed the longer term, no? Katong star nato na inanig forma. So for these two equations to be equal, kana moment generating sa Y, kung product sa marginal man, kini generic na moment generating function basta normal. So for these two equations to be normal, mapugos ta na katong sigma nato na gisulat na sigma 1, 1, sigma 2, 2, sigma 1, 2, ug sigma 2, 1 din he. Mapugos na kini na factor din ni 0 para wala man gud siya din he, no? Wala may sigma 1, 2 din he ug sigma 2, 1. So mapugos ta na dapat kana siya is equal to 0. So if and only if. So if they are independent, then sigma 1, 2 should be equal to 0. So the other way around, if we assume this And we know that the moment generating function is equal to that. So para mahimo siyang product of the marginal, from here, ang assumption nato kini man, so mahimo ni siyang 0. Mahimo ni siyang 0. And it will go back to this, we'll go back to that, and we can show that it is the product of two marginals. So mao na siya if and only if na ni siya. Okay? And this proof will show P implies Q and Q implies P. Okay? Question?
Wala ra, ma'am.
Okay. Next, as a corollary to Theorem 3.7b, ang giingon din so if y is normal, na kay y na normal, man ang covariance sa AY, BY, which is actually this part here, is 0, then any transformation sa A, Y, and BY are also independent. So kini siya ang covariance, no? Ang kini, if we are talking about pre-multiplying y by A, another by B, kung ang iyang covariance matrix kining entry na din is just equal to 0, mao man na si covariance AY BY, no? So kung ang iyang entry daw din 0, symmetric man na, then makasulti ta na si AY and si BY are independent. Now common result sa statistical inference ninyo. You have in your inference na si x bar o si s squared. Common result in inference is that x bar and s squared are independent, no? So the usual proof that is used to show that x bar and s squared are independent. So naman kay distribution sa imuhang x bar, and then kay distribution sa imuhang s, but in terms of the summation of x sub I, kini kay summation of x man . If you try to look at the covariance of x bar and s, kung tanaw nimo ang iyahang entries diha, makita nimo na ang diagonal, ang off diagonal is equal to 0. So that it will follow that x bar and s squared are independent. Now take note, ibig sabihin si x bar ma-express man nimo na siya og 1/n summation sa x, no? So ibig sabihin si s squared pwede na nimo express in terms of x pod, summation of x, pero naa kay transformation buhaton sa imong b. So unsa na matrix na imong i-multiply sa summation sa x para mahimo siyang formula sa s squared. So mao ni ang ginagamit actually kung to show that x bar and s squared are linearly independent, no? So si x bar masulat nimo as a function ax. Si s squared masulat nimo as a function bx. So a function of x gihapon na siya. So once mapakita nimo na ang covariance sa x bar and s squared equal to 0, then we say that x bar and s squared are independent, no? So mao ni usefulness ani na corollary sa inyohang statistical inference. Ma-encounter na ninyo. Okay. Next, nagisgot ta na ang normal distribution is preserved under marginal. Kining sunod na marginal distribution, kining sunod na result will be under conditional distribution of y1 given y2. So recall na gipartition nato si y as y1, y2. So kung pangitaon nato ang conditional distribution of y1 given y2, as long as na condition, no? As long as sigma 22 is positive definite. Why? Because mag-deal ang problem og inverse sa sigma 22. So, dili mag-exist ang inverse kung dili siya positive definite. So, this is the added condition for conditional distribution. Sa earlier nato na mga discussion, pwede ra non-negative definite tungod kay dili man model og inverse of sigma 22. But in here, we will deal with the inverse of sigma 22. But since this the proof of this is long, so I will start on this next meeting na. But since you are going to have your exam on Tuesday, so I will continue on this on Thursday. Okay, so you can stop recording now.